Let's take you all the way to Canada, where the country faced a very unusual event recently. 2,000 earthquakes were recorded in a single day. Scientists believe that they hold a grim warning. Recently, a particularly dramatic incident attracted the attention of seismologists and geologists worldwide. A cluster of almost 2,000 earthquakes trembled the seafloor off Vancouver Island, British Columbia, Canada, in March of 2024. This incident, which took place in one of the tectonically most active areas of the planet, revealed the intricate and frequently enigmatic processes taking place far below the ocean's surface. What specifically is causing all of these earthquakes? Is it a precursor to something even more disastrous? Do these earthquakes portend the big one, the long-feared megathrust that might wreak havoc across the Pacific Northwest? Or is this just a normal tectonic process that has no real ramifications? To answer these concerns and provide a thorough understanding of the geological, scientific, and historical elements of earthquake swarms, we will go deeply into the recent event near Vancouver Island and highlight its significance and fascination. Stay tuned as we set out on this expedition beneath the surface of the Earth to discover the hidden forces causing these tremors, consider the ramifications for the future, and comprehend what this means for the local population. It all started in early March 2024, when a series of little tremors were detected by seismometers positioned along the seafloor close to Vancouver Island. Seismic activity that at first appeared to be normal suddenly intensified into a significant earthquake swarm. More than 2,000 earthquakes, with magnitudes ranging from less than 1.0 to as high as 4.1, were recorded in quick succession over several days. The scientific world was interested in these earthquakes because of their rapid frequency and huge number, even though they were too tiny to be felt on land. A seismic swarm is made up of several tiny earthquakes that happen close to one another in space and time, frequently without a discernible main shock. This is in contrast to traditional earthquake sequences, which typically consist of one major earthquake followed by many aftershocks. Scientists are left scratching their heads as to the underlying causes of these swarms, which can last anywhere from a few days to several weeks and are characterized by constant, erratic tremors. This swarm's location is noteworthy because it happened near the Juan de Fuca Ridge, an underwater mountain range that separates the Pacific Plate from the Juan de Fuca Plate. Seafloor spreading, a process where magma emerges from beneath the Earth's mantle to build new oceanic crust as tectonic plates pull apart, is what makes this region geologically active. Additionally, the region is home to hydrothermal vents, which are distinct ecosystems supported by chemosynthesis, in which living things survive by utilizing the chemical energy emitted by these undersea fissures, as opposed to sunlight. At the height of activity, there were occasionally over 200 earthquakes each hour, which helps put the size of the swarm into perspective. It was one of the most powerful swarms ever observed in this region of the planet. Due to the magnitude of seismic activity, quick data analysis was done by researchers from Ocean Networks Canada, which runs the deep-sea monitoring station Neptune Observatory, to determine what would have caused this unusual event and what possible repercussions it might have. Understanding the broader geological context is critical before digging deeper into the causes. The Juan de Fuca Ridge is part of a complex tectonic structure that influences seismic activity in the Pacific Northwest. This ridge acts as a dynamic spreading hub, forming new marine crust continuously. The Juan de Fuca Plate, located between the much larger Pacific and North American plates, is a small but significant tectonic plate. Its subduction at the Cascadia subduction zone beneath the North American plate is known to be a major source of seismic activity, including the likelihood of huge megathrust earthquakes. This dynamic environment is directly linked to the March 2024 earthquake swarm. One theory is that the swarm might be the consequence of magmatic activity, in which rocks are fractured and a series of little earthquakes are set off by magma pushing its way upward through the crust. At mid-ocean ridges, where seafloor spreading is active, this is not unusual. Another explanation for the swarm could be that it is a result of tectonic tension being released locally along the ridge, possibly as a result of plate tectonics and movement in the area. The crust of the Earth is a dynamic, always shifting jigsaw of main and minor tectonic plates driven by convection currents inside the Earth's mantle. These plates float atop the semi-fluid asthenosphere. Mountains, volcanoes, and earthquakes are among the interactions they create as they travel, generating some of the most amazing and disastrous natural events. Often, geological regions bursting with seismic and volcanic activity are located at the limits where these plates converge. Among these tectonic hotspots is the Pacific Northwest, which comprises the dangerous Cascadia subduction zone and Vancouver Island. The rather small but important Juan de Fuca Plate lies tucked between the North American Plate to the east and the huge Pacific Plate to the west. The geological drama playing out in the Pacific Northwest is significantly enhanced by this oceanic plate subducting beneath the North American plate. The Juan de Fuca plate is gradually being consumed, a process that has been continuous for millions of years. This subduction is more than just a basic downward push. It's the force behind the building of the soaring Cascade Range, which features some of the most famous and perhaps lethal volcanoes on Earth, including Mount St. Helens and Mount Rainier. A ticking seismic time bomb, the Cascadia subduction zone is the junction of the Juan de Fuca and North American plates, among the most important subduction zones on Earth. This fault line runs about 1,000 kilometers, 620 miles, from Northern California to Vancouver Island. Here, over millennia, the stress between the two plates accumulates until it is unleashed in catastrophic events known as megathrust earthquakes, some of the strongest seismic events on Earth. These earthquakes can have magnitudes of 9.0 or above. On January 26, 1700, the Cascadia subduction zone saw the last known megathrust earthquake, as recorded in historical records. This enormous earthquake set forth a tsunami over the Pacific Ocean that devastated parts of Japan. Native oral traditions from the Pacific Northwest also tell accounts of great flooding and shaking, offering a vivid and terrible reminder of the force contained inside this fault line. Geological data, which includes coastal subsidence and drowned woods, clearly shows the damage such an event can cause. While the Cascadia subduction zone is well known for its ability to cause destructive megathrust earthquakes, it is also geologically connected to another key tectonic feature, the Juan de Fuca Ridge. This mid-ocean ridge is a divergent boundary where the Juan de Fuca plate and the Pacific plate are slowly separating. As these plates divide, magma from the Earth's mantle rises to fill the gap, forming new oceanic crust through the process known as seafloor spreading. This continuous generation of new crust is an essential component of plate tectonics, contributing to the ever-changing nature of the Earth's lithosphere. Seismic activity is frequent on mid-ocean ridges such as the Juan de Fuca Ridge. Typically, this activity is moderate, caused by the straining and breaking of the marine crust as new materials are generated. These minor earthquakes are a normal part of the seafloor spreading process and usually cause little concern. However, the recent earthquake swarm along the Juan de Fuca Ridge has piqued the interest of geologists and seismologists. An earthquake swarm is a series of seismic events that occur in a single location within a short time. While most swarms are harmless and result from normal tectonic processes, the strength and duration of this current swarm indicate that something more sophisticated is going on beneath the surface. Scientists hypothesize that the swarm could be a sign of magma activity beneath the crust. Magma can distort the Earth's crust, resulting in greater seismic activity as the rock above it splits and shifts. This type of activity is frequently seen preceding volcanic eruptions, although it can also occur in non-volcanic environments. In the case of the Juan de Fuca Ridge, magma mobility could be linked to the ongoing process of seafloor spreading, in which new magma rises to form fresh oceanic crust. The exact cause of the swarm remains unknown. More research and monitoring are required to properly understand the consequences of this seismic activity. Another hypothesis is that the swarm is a precursor to a larger seismic event. While earthquake swarms are rarely directly related to significant earthquakes, they might occasionally suggest that tension is building up in a fault line, increasing the likelihood of a severe quake. In a geologically active region like the Pacific Northwest, even small increases in seismic activity can cause alarm. The Cascadia subduction zone in particular is known for its ability to generate some of the world's most violent earthquakes, with magnitudes of 9.0 or higher. The last known megathrust earthquake in this region happened in 1700, and its effects were noticed as far as Japan, where it caused a disastrous tsunami. Earthquake swarms are particularly noteworthy because they deviate from the usual pattern of seismic activity. In a typical earthquake sequence, a big quake, known as the main shock, is followed by a succession of lesser aftershocks. Swarms, on the other hand, are made up of a series of tremors of varied magnitudes that occur over a short period, frequently without a distinct main shock. This can be perplexing for both scientists and the general public since it contradicts common assumptions about how earthquakes should behave. The study of earthquake swarms is a relatively new field of research, and scientists are still trying to figure out what causes these phenomena. Swarms can form for a variety of reasons, including magma movement, fault slip, and fluid injection into the crust. Because swarms lack a single, obvious trigger, they can be difficult to predict and monitor. However, scientists have observed that swarms frequently arise in geologically active places, such as volcanic zones and tectonic plate boundaries. The ongoing investigation of the Juan de Fuca Ridge swarm exemplifies the scientific community's efforts to understand these complex processes. With modern monitoring technology, researchers can gather real-time data on seismic activity, crust deformation, and other signals that may provide insight into the underlying causes of the swarm. They are just normal geological processes, especially in mid-ocean environments. With the prospect of a mega-thrust earthquake looming large in places like the Pacific Northwest, it is imperative to comprehend swarm behavior and potential repercussions. To gain a deeper understanding of the significance of the recent swarm, it is imperative to examine the historical trajectory of seismic activity within the region. Seismic activity in the Pacific Northwest has a long and complicated history. This area has seen its fair share of geological drama, from strong mega-thrust earthquakes to minor tectonic tremors. The main source of this seismic activity is the Cascadia subduction zone, which is located right off the coast. Some of the most catastrophic earthquakes recorded in the geological record have been caused by it. The aforementioned Cascadia earthquake in 1700 is one of the most significant historical occurrences. With a magnitude of around 9.0, this mega-thrust earthquake broke the subduction zone's whole length, resulting in extensive damage and a wave that spanned the Pacific Ocean. The scale of this catastrophe is confirmed by geological evidence such as sediment deposits and ghost forests, which are stands of dead trees destroyed by sudden ground subsidence. Indigenous oral histories from coastal areas also mention a tremendous tremble that was followed by a huge wave, underscoring the profound cultural memory of this catastrophe. At least in terms of significant earthquakes, the Cascadia subduction zone has not had many since then. This silence, nevertheless, does not always feel comforting. Indeed, it might indicate that tension is progressively increasing along the fault, preparing the ground for yet another disastrous incident. The anticipated recurrence period for mega-thrust earthquakes in this area is 200 to 800 years, indicating that the location is currently within the window of time where a major earthquake could occur. The Pacific Northwest is home to multiple fault systems that, in addition to the Cascadia subduction zone, contribute to the seismic activity in the area. Numerous smaller faults, as well as the Portland Hills and Seattle faults, are scattered throughout the terrain and can cause powerful earthquakes. Even while subduction zones are more likely to create big earthquakes than these faults, heavily populated places are nevertheless at serious risk from these faults. Additionally, the area is known for episodic tremor and slip (ETS) episodes, which are a relatively new finding in seismology. The subduction interface experiences sluggish deep-seated slip during these occurrences, which are accompanied by low-frequency tremors that are challenging to pick up with conventional seismometers. Although ETS events don't produce audible surface shaking, they are believed to be a crucial component of the subduction zone earthquake cycle. According to some scientists, ETS events might contribute to the loading of stress onto the locked section of the fault, which could later result in greater earthquakes. This background makes it abundantly evident that the Pacific Northwest is a geologically active area with a high seismic hazard risk. The current spate of earthquakes in the vicinity of Vancouver Island is merely the most recent development in a lengthy and intricate tale of tectonic activity in this region. However, what does this swarm reveal about the tectonic plate conditions in the area right now, and how does it relate to the overall picture of seismic risk? The ramifications of the recent spate of earthquakes off the coast of Vancouver Island are presently being evaluated by scientists. The swarm itself may not be dangerous right now, but it raises serious questions about the underlying geological processes and their potential consequences. With more than 2,000 little earthquakes, this event might just be a normal part of the seafloor's natural spreading process. Juan de Fuca Ridge and other mid-ocean ridges are active locations where new oceanic crust is constantly created. Magma rises from underneath, cools, and solidifies during this process, gradually forcing the older crust apart. As a result, little earthquakes are produced as the just-created crust adjusts. If this swarm is simply a sign of normal seafloor spreading, there may be no need to panic just yet. It could mean that the ridge is operating as it should. The size and frequency of this swarm, according to some scientists, may point to more intricate processes at work. There may be significant magmatic movement beneath the bottom, which would explain the high seismic activity. Small earthquakes and fractures can result from the pressure that magma builds up inside the crust as it pushes higher. Such action frequently occurs in volcanic systems before an eruption. However, this may indicate an increased phase of seismic activity at tectonic locations such as the Juan de Fuca Ridge, which could result in greater occurrences. Another idea is that the stress transmission between the Juan de Fuca plate segments is connected to this swarm. Within tectonic systems, an earthquake's released stress can reorganize the plate, possibly setting off further earthquakes in adjacent areas. In the upcoming months, there may be further seismic events if this swarm signifies a major release of stress. If future activity moves toward more populated coastal areas, then there may be concerns associated with such a scenario. Is this swarm associated with the Cascadia subduction zone, a significant fault line extending from Northern California to Vancouver Island? This is perhaps the most troubling question. The Pacific Northwest might be destroyed by gigantic mega-thrust earthquakes, which are infamous for having the capacity to occur in the subduction zone. Despite the swarm's distance from the Cascadia Fault's-locked region, some experts believe that elevated seismic activity near the Juan de Fuca Ridge may have an impact on when a mega-thrust earthquake occurs in the future. The basic hypothesis is that there could be a transmission of tectonic force from the ridge to the subduction zone, which could influence when the next big one happens. Even while there isn't any concrete proof connecting the swarm to the Cascadia Fault, study is still being done to better comprehend any potential linkages. A deeper comprehension of the formation of the Earth's marine crust is one of the major scientific discoveries made possible by researching occurrences such as the Juan de Fuca earthquake swarm. One of the basic mechanisms of plate tectonics is the process of seafloor spreading, which propels the formation of new crust along mid-ocean ridges. When tectonic plates separate at divergent borders, like the Juan de Fuca Ridge, seafloor spreading happens. Magma from the mantle rises to fill the void left by the plates separating, cools, and solidifies to form a new oceanic crust. The older crust is gradually pushed away from the ridge by this process, which is what causes the ocean floor to continuously regenerate. As you move further from the ridge, the age of the oceanic crust increases, with the youngest crust being found closest to the spreading core. Magma migration beneath the seafloor is a dynamic and intricate process. The pressure that magma puts on the surrounding rock as it rises through the crust causes it to fracture and crack. The magma can travel via these fractures to the surface, where it solidifies as lava. The different layers of basalt, gabbro, and peridotite that make up the unique layered structure of the oceanic crust are created by the recurring cycle of magma injection, fracture, and lava flow. This magmatic activity is intimately associated with hydrothermal vent systems, which are located along mid-ocean ridges. In addition to producing new crust, when seawater seeps through cracks deep into the crust and is heated by the underlying magma, vents like these are formed. After that, the superheated water returns to the surface, bringing a diverse array of dissolved minerals with it. Known as black smokers, these hydrothermal vents are home to unique ecosystems that thrive on chemosynthesis rather than photosynthesis, relying on the chemical energy from the vent fluids instead of sunlight. The hot, mineral-laden water meets the cold seawater, and the minerals precipitate out, forming towering structures. These hydrothermal systems were probably affected by the latest earthquake swarm. The crust's trembling and cracking may modify fluid movement, modify the chemical composition of vent emissions, or even momentarily close or open up new vent sites. The swarm offers a rare chance for scientists researching these ecosystems to see firsthand how life adjusts to quickly shifting environmental conditions. More broad research on magmatic processes at mid-ocean ridges and seafloor spreading aids in the understanding of the larger-scale dynamics of the Earth's lithosphere. Scientists can learn more about the processes that drive earthquakes and volcanic activity, the movement of tectonic plates, and the cycles of crust creation by keeping an eye on occurrences like the latest swarm. These discoveries not only broaden our knowledge of Earth's geological past but also aid in our readiness for potential threats in the future. The most difficult task in seismology is determining the precise location and time of an earthquake. Although our understanding of the factors causing seismic activity has greatly advanced, it is still difficult to predict the exact time and location of earthquakes. Despite this uncertainty, ongoing data collection and sophisticated monitoring methods are improving our capacity to identify trends and improve prediction models, providing important information on seismic activity. Ocean Networks Canada's Neptune Observatory is a major participant in seismic activity monitoring in the Pacific Northwest, including the Juan de Fuca Ridge. This cutting-edge facility is located far below the surface of the water and is a component of a larger network of sensors that gather data in real time on a variety of dynamic activities. A variety of monitoring instruments such as hydrophones, pressure gauges, and seismometers are available at the observatory. These instruments allow for a thorough understanding of the tectonic processes taking place along this important fault zone. The Neptune Observatory's continuous monitoring projects offer invaluable insights into the movement of tectonic plates, the reaction of underwater ecosystems to seismic events, and fault line behavior under stress. Understanding these dynamics is essential, especially in the Pacific Northwest, where tectonic plate convergence generates the likelihood of catastrophic mega-thrust earthquakes. Among the strongest earthquakes ever recorded, these might destroy whole communities in the vicinity. Improving early warning systems that can provide advanced notification of an approaching earthquake is one of the main objectives of this research. While pinpointing the exact time of an earthquake remains elusive, early warning systems can provide crucial seconds or even minutes of lead time before shaking begins. This could be invaluable in terms of mitigating the loss of life, allowing people to take cover, automated systems to shut down critical infrastructure, and emergency response teams to mobilize. Swarms of earthquakes like those off the coast of Vancouver Island could be analyzed as a potential precursor to larger seismic events in the future. In conclusion, while the earthquake swarm near the Juan de Fuca Ridge may be an example of typical geological activity associated with seafloor spreading, it emphasizes the complicated and constantly changing tectonic processes in the Pacific Northwest. Although swarms by themselves are not always signs of an impending mega-thrust earthquake, they offer a chance to improve our knowledge of the area's seismic risks. The necessity of constant monitoring and preparedness cannot be overstated, given that the Cascadia subduction zone remains locked and capable of unleashing a potentially catastrophic event in the future.